one of the things that we've been doing up until this point is we've been giving you guys, especially the second half of this semester, so we've been giving you guys a bunch of tools to work with data sets. And like any tool, you have to use the right tool in the right situation, right? Like you wouldn't use a hammer to put in a screw. You might not. When you're really stuck, all you have is a hammer. You use a hammer, but you realize that that's not what you want to do, right? So we want to use the right tool for the right job, and that's true in statistics just as much as anything else. So let's talk about like the couple of tools that we've learned about so far. Okay, the way that we apply these various tools is dependent on what kind of data that we're working with. Like for instance, I'm just keeping an eye on the chat box here to make sure nobody's having problems with hearing us. So for instance, if we have a situation where we have two categorical variables, let's say something like gender and HIV status, like positive or negative HIV status. Okay, they're both categorical, right? Yes or no, male or female, right? And we know usually what kind of table do we set up for those? We set up crosstabs, right? Like we might put gender in here, male, female. We might put status, like a positive or negative here, very much like we did with our diagnostic tests, right? So this is a 2x2 table. We need a tool to work with that. We know that we can't use an average, right? We can't use something that's intended for numerical variables like average to determine the average HIV status. There's no such thing. You have HIV, you're infected or you're not infected, or you're male or you're female. In general, you have two categories that you're working with. You can have more than two categories, right? But for a moment, let's just assume we're using two categories. So what test can we use there? What's that? Chi-square. Exactly. We just learned that last week. So we have a tool where we can use to determine whether there is an association between one variable, gender, and the other variable, HIV status. But we got other tools too, right? Tools that give us a little bit more information about the magnitude of the difference, right? You remember what those were, right? If I had 10 out of 10 and 90 that weren't, and out of 100, 10 out of 100, what is that? Right, 10 out of 100 would be the risk of being a male and having HIV, being HIV positive. So you could have risk, and you could have relative risk. You can compare the risk for females to the risk for males, right? And that might be 10% over 20%. Males would be protected. The gender male would be protective. Okay, so the other thing besides relative risk, something that you see show up in studies a little bit more, is another way of calculating that, and that's the odds ratio. Okay, so all of these things, odds ratio, relative risk, chi-square, they're ways of working with categorical variables. We wouldn't use it for numerical variables, not unless we change the numerical variable into a categorical variable. You do that sometimes, right? So, for instance, if community health survey they're using as a data source, if they say something like, for instance, how much fruit do you eat, and they have categories, different categories, like, or people reported the exact number that they ate. You might say that, let's say, 2 servings or less per day is not very much fruit, and 3 servings or more is an adequate amount of fruit. So you might convert that into categorical variable, like low or low or adequate, low or adequate, 1 or 2, right? So this way you can manipulate the data to become categorical. But the test is intended for categories. Okay, so now what about if we have numerical data that's factored, broken up into groups as categories? For instance, let's say we were looking at males and females, but we were not comparing HIV status, which is a kind of a yes or a no or categorical variable, that we're comparing, say, blood sugar levels. Okay, so blood sugar levels are a numerical variable. So I have male and female, gender is categorical, but we also have a numerical variable involved. And so we could find the average blood sugar level for males, we could find the average blood sugar level for females, and we can compare the two of them to see if we think the population of males has a higher average blood sugar level than the population of females. So what kind of test would we use there to compare two means? Right? What do we do there to compare the two means? Right? T-test, right? Remember the T-test? Just the number of standard deviations apart that the two of them, we use a T-test to compare the two of them. Okay, we can do that using SPSS. We can do the calculations ourselves in Excel, but T-test is what we would use. And if you remember, when we did the T-test in SPSS, we had two boxes that were set up, like the list of the variables, and we had a box that put in our numerical variable. We moved our numerical variable, and then we had another box that was for our factor. Our factor was the groups that this was broken up into, or in other words, the categories that it was broken up into. And when we moved the numerical variable into this box for analysis, for finding the means and the t-score and so on and so forth, when we moved that into there, we also had to move a categorical variable in, like gender, into the other box. And what did SPSS ask us for when we did that? Remember, a little window popped up, and it said, "Give me the number. Give me what represents these the categories within this categorical variable, like 1 and 2, 0 and 1, A and B. Like, what are the categories that I'm working with?" And you remember how many spaces that had? That only had 2 spaces you could fill out, right? Because a t-test is designed for comparing two means: the means of males versus the means of females, the means of basketball players versus the means of football players, so on and so forth, right? 2 groups. Okay, so now, unfortunately, that's not always the case, right? Sometimes we're going to be in a situation now where we're dealing with a numerical variable, right? I'm going to let's see, I'll pick one out. Let's see, average. We're talking about weight for a numerical variable. Well, in this case, maybe we're dealing with a situation where we have more than the categorical variable, the factors that we're going to break it up into, right? Factors we're going to break it up into have more than 2 values. For instance, instead of male and female, right? Maybe the categories might be ethnicity, for instance. Let's say the categorical variable is ethnicity. Well, there's more than 2 ethnic groups, right? There's white, there's Hispanic, there's black, there's Pacific Islander, there's so on and so forth. I could come up with more if I wanted to, right? But we have 4 categories. So how are we going to compare the average weight, or whatever, this could be any numerical variable, the average weight, the average blood sugar, the average let's say blood pressure. Let's compare the average blood pressure to a population of white subjects, Hispanic subjects, black subjects, and Pacific Islanders. Asian and Pacific Islander. Okay, so we get a few more people in there. Okay, so let's say we want to compare the means of those 4 groups. Well, we could use a t-test here, couldn't we? Right? In other words, I could compare whites to Hispanics. I could use a t-test to do that. Right? I could compare whites to blacks, t-test. I could compare whites to Asian Pacific Islanders. Right? Now, the only problem now is I've only covered 3. There's 4 groups. I've only got 4 possible values for that categorical variable, but I've only covered 3 possibilities so far. Now, there's still more, right? I haven't compared Hispanic to blacks. I haven't compared Hispanics to Asian Pacific Islanders. I haven't compared blacks to Asian Pacific Islanders. So in other words, the number of different combinations I have is 3 times 2. And we have 3, 2, and 1. So we have 6 different possibilities here, right, for doing a t-test. Now, usually when I set up a t-test, what's the acceptable level of error that I have for rejecting the null hypothesis? 5%, right? 0.05, right? Okay, so now if I run that test 6 times, what happens now? You guys ever heard of Russian roulette, right? They spin the thing and they pull the trigger and stuff like that. You do a t-test often enough, right? You're going to be wrong, right? So we have a problem with doing t-tests. First of all, number one, it's going to be very tedious to repeat this analysis over and over and over again, right? So we might be working with another situation where, let's say we wanted to compare the average average age of marriage, average age of first marriage in all 50 states. Well, gee, we have 50 states. Can you imagine how many t-tests we'd be doing, right? So that's a little bit of an exaggeration, but you can see that we need a test that'll help us compare groups that are normally distributed, but that has more than two categories that we're concerned about. Okay, so now that's where analysis of variance comes in. I'm gonna kind of play a video I put together a while ago. It's going to be okay here, but I'm going to narrate it because I don't want to have to deal with the sound and stuff like that. So I deal with connecting to the sound here and getting the sound to work. So I'm going to narrate it. I'm going to pause it as we go through it so we can take a look at it. Hopefully the guys online will be able to see it as well. Let me just see where I lost it now. Okay. Maybe it was... there we go. Okay. Okay, let's see if we can get it play. I'm going to ask the guys online how well this works.
We're going to use analysis of variance.
Remember I was talking about that trip to
except this time we're going to be looking at 3 or more groups. Okay. This past spring, I was lucky enough to get
that was
to the
about 3 years ago. Spectacular. If you get a chance to go down there, it's absolutely beautiful.
Something very interesting.
Literally
they filled an
100 to
entire
200
field with
cherry
these
trees.
Beautiful cherry trees. And there were just so many of them, and they were so close together that it was hard to distinguish the blossoms from one tree from the blossoms from another tree.
Where'd that go?
There were a variety of trees that were present at the Brooklyn Botanical Gardens. Some of the trees were wide and very full of blossoms. Others of the trees were much...
Can you hear that? Some of you can, some of you can't. Okay, the idea here is that there's a lot of different variety of trees there. Some of them are, like tall and narrow. Some of them are spread out. They're very wide. That looks like something you've seen before. We'll talk about
narrower. I noticed that if the trees were very wide, if the blossoms were really spread out, that in order to be able to distinguish between individual trees, the tree trunks had to be very far apart. On the other hand, if the trees were very narrow, the trunks didn't have to be that far apart in order to distinguish between individual trees. I further noticed that the trees were symmetrical. The trunks were in the middle of the trees, and more of the blossoms were towards the center of the tree, fewer were far away from the tree. I realized that there's something else that has those same characteristics.
Right? Aren't they kind of like normal distributions? If you look at the distribution of leaves on them, right? Am I wrong? It kind of looks like that, right? Most of it, there's more leaves in the center, there's fewer and fewer as you get to the outside. So it's almost kind of like a normal
middle of the distribution. And more of the values are close to the mean, fewer are further away from the mean, and it's symmetrical.
Only
Here,
4 minutes of this
we see 3 groups represented on the top and on the bottom. The variability is the same for all of these groups.
Yes, let's take a look at what happened here. These means, imagine the trunk of the tree is the mean, right, the middle of the tree. These means on the bottom, the means are spread out, they're far apart. So even though the variability is the same, take my word for it, I don't know if it's optically, it looks like that. The variability of spread is the same on top as it is on the bottom. The fact that the means are spread out make it easier to distinguish between the groups, between the trees.
So it's hard to distinguish between the 3 groups. On the bottom, the means are further apart, making it easier to distinguish.
It's kind of like a ballpark,
Here, the means are the same, but the variability for the groups on the bottom is much smaller.
Right? See, in this case, the means are close together, right? And they're the same. That means they're not different. But in this case, the variability on the bottom is much narrower. Those are those tall, narrow trees, right? So the spread makes it, the fact that they're not spread out as far, even though the means are closer, make it easier to distinguish between the groups.
Even though the means are the same, we can distinguish easily between the 3 groups in the bottom set. Let's create...
I love creating, make believe that you're inventing a statistic now. Okay, so you want to describe this. You want to figure out how you can apply this this device that you've noticed about the distance between the means and the variability?
A new statistic that we're going to call F. F is going to be the ratio of two numbers. On top, the numerator is going to be the variance between the means in several groups. The larger the variance between the means of the groups, in other words, the further apart the means are, the larger that ratio F is going to be.
Okay, so what we're after here is getting a number that describes how easy is it to tell these groups are really different. Okay, so we want that number to be bigger when we can tell that they're different and smaller when we're not certain that they're different, right? So we had set up a ratio. So the number on top represents how far apart, what the variability between the means is.
On the bottom of this ratio, we're going to put a number that represents the variance within the groups.
Okay, in other words, the bottom number is a number that represents the variability within each one of the three groups. We want that number to be small because when the numerator is a big number and the denominator, the bottom, is a small number, we get a bigger number overall. So each one of these things is gonna work the way that we want it. We want a small variance within the groups, but we want a big variability between the means.
As the variability within the groups becomes smaller and they become narrower, F also becomes larger. Our statistic F represents a ratio of the variance of the means over a number representing the variance within the individual groups. The further apart the means are, and the narrower the groups are, the easier it is to distinguish between the groups and the larger the value of F. F has a probability.
Another distribution, right? Every time we seem to do this, we seem to associate a distribution with these functions. In this case, this is happens to be the safe shape of this distribution. Similar to chi-square, for different numbers, different sample sizes. Now remember, we can have many means, right? Or we can have very few means. So we have different degrees of freedom. So again, like chi-square, we're going to have a table where we're going to have to apply the degrees of freedom in a couple of ways so that we get the right distribution. Right now, we're just dealing with those three means.
Distribution associated with it. In this graph, we can see that there's a region that if F is large enough, we can be safe in saying that the means of the groups are different rather than being from the same population.
Okay, so we're looking for that F value to be so large that it's unlikely that all three of those groups would be from the same population. How unlikely? Well, we're willing to accept any result that has less than 5% chance of being from that population. So we only want that little corner at the end there to be 5% or less. Okay, so what do we call that value of F again? Just like chi-squared, what do we call the value we have to exceed to reject the null hypothesis? Anybody remember? What kind of value? Critical value, right? Okay, so we want that we got to look up that critical value. We want F to be bigger than that. Was that a question? Did I miss a question? Okay.
Our lab exercises this week,
yeah, we're going to
use the F statistic to determine when we can distinguish between means of three or more groups.
Okay.
In this chapter, we'll find a demonstration of using
I'll explain chapter later on, why it said chapter. Okay, so this video, I got a link to it online if you want to see it again. There's also a couple of videos that show us going through the calculations that we're going to go through right now. So we're going to try one simple example of manually calculating analysis of variance. Okay, and if you go to Blackboard, there's an Excel data file. It's in that folder number 1 that says ANOVA Excel demo.xlsx. I'm going to open that up. And if we're lucky, you guys can go along. You can do it along with me. Now, for the most part, it's going to be relatively rare that you're going to be in a situation where you're actually going to calculate this manually. I just think it might be worth just doing this one time to go through the process and take a look at it. Remember, we're talking about the variability, these measures of variability. Well, when we deal with a normal distribution, what's our measure of variability that we use? Well, usually we're looking at standard deviation, right? Well, standard deviation is just the square root of the variance, right? And how do we get it? You remember in the beginning of the semester we did in Excel, how do we get the variance? We take the sum of the squares of the differences, we add them all together, and we divide by n minus 1. N minus 1 is kind of like a measure of degrees of freedom. So we're going to do this now. We're going to do it twice. We're going to find that measure of variability. The sum of squares divided by the degrees of freedom. We're going to find that measure of variability for the means, the values, the mean values between these things, and the variability within each one of the groups as well. Okay, so let's take a look at it. Let's give this a try. So if you open this up, I'm going to blow this up so we can see it better. If you open this up, we have three groups. I just named them Group 1, Group 2, and Group 3. I think in the video, in the other version of this video, I think I gave them different names. But there's three samples. Okay, now anybody remember what the assumptions were for analysis of variance? What about, I'm sorry? No, yeah, we want each of the populations to be normal, right? What else was there? What about how it's sampled, right? Independent and random, right? We want that. And what about the variability of each of the three groups? Can they be different? We want the variability to be reasonably close to one another, right? Homoscedasticity. I won't bother to look it up. Okay, so remember that word? Homoscedasticity, right? We want the variability to be roughly equal in the three populations. Okay, so those are the three assumptions, and it looks like they're reasonably, like there's a shot that we might achieve that. Remember, we're really interested in that population, not necessarily in the samples, but we're concerned if the samples are really skewed also. Okay, so let's take a look at this. First thing I'm going to do is I'm going to calculate the mean for each one of these three groups. Okay, so the mean for this first group is equal to, I'm going to click in down here. Mean is equal to the average. What happened here? See if I can't do this here. Oh, I know what I did here. Okay, let's see. How should I do this here? Okay, I'm going to copy this down here. Control C, I'm going to paste it here. And I'm going to do the same thing here. I had another version of this where I had the formulas embedded to save a little bit of time, but, I'm sorry. I just made a mistake there, didn't I? That's the second group. Oh, no, now that's the third group. I really messed this up. Okay, let me take that and put that there. Okay, so despite my stumbling here, this is the first group. I just copied the values. This is the second group. That's the third group. I'm going to find the average for each one of them. Okay, there are my three averages. Okay, average of the first group is 1.8, second group is 3.4, third group is 4.4. Well, the average is pretty different. Those are my tree trunks pretty far apart. I'm thinking maybe I got a shot at demonstrating that there's a difference between these three groups. Maybe this is a good time to step aside for a moment and say to ourselves, what are we trying to prove here anyway? Right? We have to set up our hypothesis test. Right? So our hypothesis test, first thing, we already went over our assumptions. So what is our hypothesis test in this case? What am I looking to demonstrate about Group 1, Group 2, and Group 3? And the populations that they represent. Right, we want to prove that they're not equal. So we start with a null hypothesis, which is that the means of the three groups are equal. Mu1 is equal to mu2 is equal to mu for group 3. So what's our alternative hypothesis? At least two of them are not equal, right? Okay, not all three necessarily, but perhaps, but at least two of these are not equal. Okay, so now we're going to calculate the variability. One thing we want is a variability within the groups, and then we want the variability between the groups. So let's do within the groups themselves first. So the first thing I'm going to do is I'm going to do what we did in the beginning to calculate variability. Okay, I'm going to find I'm going to copy X bar here equals 1.8. Remember, I'm going to put dollar signs in front of that because I want this to be absolute addressing. So when I copy it down, it'll give me the same number. Whoops, the orange spot there. $B, $16. Okay, just like we did before. I'm going to fill down. Okay, I'm going to do the same thing here. Equals, that's going to be B24, dollar, and oops, dollar. Okay, and I'm going to copy that down. And I'm going to go down here to this last group, equals the mean that's in that cell, happens to be in that, oops. How did I do that? Dollar and dollar. You guys online doing okay? Video was pretty choppy, right? Okay, at least you heard my voice and you heard my voice repeating most of what the audio was in the video. Yeah, unfortunately, GoToMeeting has a really nice way of playing back video, but you can only do it on PCs. You can't do it on. They don't like Macs to GoToMeeting. So the audio gets pretty choppy. But again, there's links on Blackboard to that video if you really want to see it again. Okay, good. All right, now next thing we're going to do is find the differences between each value and the mean. Okay, it's going to be x minus the mean, and I'm going to fill down. Okay, you know there's various ways you could fill down if you want. Grab the corner. Okay, let's see if I can get it to work here. Yeah, I never managed to make that work. Actually, if I hit enter, I think it'll work better. Nope. Yeah, there it goes. See, I don't have the dexterity anymore for that. That's why I go up to the menu. And I'm going to fill down. Okay, this is all of the differences between. We know that if we just added these up, these differences come out to 0. So we're going to square them so that we don't lose the differences. Oops. It always comes up at the wrong time. Okay, so we'll square them. I happen to start with the middle group there. You can start anywhere you want. Oops. Let's see. And I'm going to fill down. Okay, and finally group 3. Square the differences. Okay, and if I add up these values for each one of these groups, I have the sum of the squares of the differences within each group. That's within the groups. Okay, so now let's see if I can go over here and take a look at this. And you want to know something? Here's a formula I had set up before. If you look in here, that's E16 plus E24 plus E32. I was going to say, let's go over here where it says sum of the squares of the differences within the groups, right? Well, I've already got that formula in there. So as soon as I calculated what E16 was at 2.8 and the 5.2 and the 17.2, it filled it in. If it hadn't, you could have done it yourself. Just put an equal sign in there. I'll click in there so you can see that up at the top there. E16 plus E22 plus E32. Okay, so now the number of degrees of freedom for this. Well, the number of degrees of freedom, if we were looking at a group with a sample with 5 subjects in it, how many degrees of freedom would that be? 4, right? N minus 1. Well, now we have 3 groups. Each of them has 5 in it. So what do you think that might be? Well, since there's 3 groups, it's going to be the number of subjects total minus the number of groups. So we got 15 total subjects minus 3. So the degrees of freedom are going to be equal to 12. Okay. So the mean sum of squares within the groups, I'm calling it mean sum of squares because I divided by the number of degrees of freedom, which is really sample size minus 1, right? So we're calling that mean sum of squares. That mean sum of squares, that got filled in here automatically for us. That's the bottom of our equation. That represents the variability within the groups. We want the variability within the groups to be a small number because it's in the denominator. It's on the bottom of that fraction. Okay, so now let's calculate the top of that fraction. Okay, so the overall mean, right? Okay, let's see if we can't figure out the overall mean here and see why I didn't fill it out. Let's see. Sum of B11, H reference. Why it didn't work there? Let me see. B11 through B15 plus the sum of, what is that pound reference? Where'd that come from? Sum. Oh, I get it. That's a little bit of a mess there. See if that one's right. 27 through 31. And this one should be 19 to 23, is it? 19:23. Thank you. Let's see if that works. Got to close the parentheses, I think. And that's otherwise all wrapped up in there. I'm going to hit enter. I'll roll the dice. Oh my God, what happened there? It's a circular reference. What did I do there? All right, tell you what I'm going to do. Yeah, that's a good idea. Let me try and figure this out again. The sum, that sum's right. This sum is right. So the sum, I'm gonna do it. Whoops, I still got a apostrophe in there. I'm gonna just overwrite. I'm just gonna go down there and not depend on myself to get it right. I'll just do that. Okay, you see what's happening there? We're adding up all of the values in the groups and we're dividing by 15 to get an overall average. I think it worked. It worked. Okay, 3.2. That worked that time. We just added up all of the values, all 15 values, divided by 15 to get the overall mean. Okay, so the overall mean is 3.2. The individual means are 1.8, are 3.4, and are 4.2. So if I subtract the overall mean from each one of those values, I get negative 1.4, 1, 0.2. So this is the differences between the individual means versus the overall mean. Okay, now I'm going to square that, and there's actually, this would be a pretty small number that we're going to put in that numerator. There's actually, I'm really looking for all of the differences for all of the values. So there's actually 5 values in each one of the groups. So I'm going to multiply the squared differences by 5, and the total differences squared are 9.8, 0.2, 7.2, which adds up to 17.2 is the sum of the squares of the differences between all the values and the means, right? All the values between the means, without regard to the individual groups. So that number winds up going down here, and it did transpose down there. There's a formula built in this, so it would appear there. Okay, so now how many degrees of freedom do you think we have here? Now we're looking at those 3 groups now, right? Those 3 groups, right? There's 3 groups. The degrees of freedom for the differences between the means is going to be equal to the number of groups minus 1. And that's going to be number 2. Okay, I'm going to hit enter. Okay, and that comes out to 8.6. So the number that's on top here, the mean sum of squares between the groups, is 8.6. The number for the mean sum of squares within the groups is 2.1. You guys can go through this a little bit more carefully later on. And also in the video, I go through this. Okay, so I don't want to kill too much time on it because you're really not going to do this way. So we wind up with an F score of 4.09. Okay, we're going to do this exact problem in SPSS, in a moment. But that's the number that we get. Now, does that number tell us anything at this stage? Right? It's a nice number, 4.00 sounds nice, right? If we're, right? But does it actually tell us anything? No, we have to compare it to the critical value, right? So we have to know whether that number in this case, with this size, with this number of groups, and with this number of subjects within each group, whether or not that number is large enough for us to get that, whether that number would represent the number that's so large that it would only occur less than 5% of the time if there was no difference between the means. In other words, if there was a less than 5% chance of me being wrong if I reject our null hypothesis, or you guys being wrong, because you guys, I'm going to blame it on you if you're wrong. So I'm not going to take the blame for this. So we're going to get that. We're going to go to, on Blackboard, we have a copy of a table. Okay, and let's see if I can't find it now. Okay, let's see. Go back here on Blackboard. And this is from a different textbook than ours, but it's going to look basically the same. Now, in this case, we have 2 degrees of freedom that we're working here, right? The degrees of freedom based on the number of groups, and the degrees of freedom based on the number of subjects, within all of the groups. So the degrees of freedom within the groups, most of these charts, most of these tables are labeled between or within, right? So it's easy to distinguish. This one happens not to be labeled that way. It just says degrees of freedom 2 and degrees of freedom 1. Okay, so kind of leaves you, there probably is a table that's not included here, or legend that's not included here. But if I look here, let's see, 1, 2, 3, 4, 5, 6, 8. But if I look in the vertical column, 23, 25, I can pretty much assume that the vertical column represents the degrees of freedom within the groups, the bigger number, and the horizontal column represents the degrees of freedom between the groups, between the means. And what was the degrees of freedom between the means? 2. Okay, so we're going to work in this column, 2. And we're going to go down to the degrees of freedom within the groups, which was 12. So the critical value for us for the analysis of variance is 3.89. What did we calculate it to be? Right. So what's our conclusion? We reject the null hypothesis. There's less than 5% chance that we will be wrong if we reject the null hypothesis. Okay, let's give it a try in SPSS now. Now I'm going to open it up to the same data set in SPSS. Okay, the first thing I want to focus on in SPSS is I want to focus on how the data is presented compared to what we saw in Excel, because it's quite different, right? In SPSS, each column represents a variable, right? In Excel, we could have put the variable and we could have spread it around any way we wanted. But in this case, each column represents a variable. So in the variable group, which is, what is that? Is that the numerical variable or the categorical variable group? That's categorical, right? Group 1, group 2, group 3. The numerical variable was the measurement that we took, that 1, 7, 3, and so on. Okay, if I go to the variable view, we can actually see that. Okay, and actually it has both down as nominal, and that's because the numbers are so small. SPSS made the assumption that the measurements, because I think the highest number was like 6 or 7, right? So it kind of made that judgment. And you want to know something? Sometimes SPSS will interfere with you running a calculation if it gets the type of variable wrong. It may not let you run the calculation. So just to prevent that from happening, I'm going to change this to scalar for measurement so that SPSS now understands it's a numerical variable. Okay? Okay, let's go back to data view. And in the data view, of course, if I'm sorry, I should stay in the variable view for a moment. If I go into the variable view, let's see if this is coded already. I'm going to go into the values column, click on it, and actually, those are the old group names I had. I'm going to change those right now. Okay, I'm going to click on Fred. I'm going to change that to group 1. Okay, I'm going to click on 2, and I'm going to change that to group 2. You don't have to if you don't want to. I just want to do it so things are clear. group 3. Click change. You got to click change and then click OK, or it won't take. Okay, so now if I click in there again, I'll get what I expected. Okay, it's a categorical variable, and the 1 represents group 1, 2 represents group 2, 3 represents group 3. Okay, I'm going to go back to my data view, and just to confirm that, I'm going to go up here to view and turn on the toggle for value labels, so I can see which ones are group 1, group 2, and group 3. And you can see the values here correspond to, there's 5 values for group 1, and they're the same ones we were working with before, and 5 for group 2, and 5 for group 3. Okay, and it is important that this is laid out this way, because if it, depending on how we lay it out in Excel, if we're trying to import it into SPSS, it may not be formatted properly for us to understand how it's displayed. Okay, Jay, are you okay with sound there now? So I want to check with the guys online. Okay, I think you guys are okay with the sound. I did not lose sound. Okay, good. Okay, good, no problem. Every once in a while, someone complains that they lost the sound, but we're on the internet, so what happens if a little bit of data goes astray or something like that, or you can lose a connection or something? And I can usually tell whether it's us or them, because if it's us, everybody's complaining. If it's them, it's usually one person complaining, and I think we got it straightened out. Okay, good. All right, and again, the recording's on, so we should be okay with that. All right, so now let's go ahead and do this analysis. So let's go up to Analyze, as we normally would. Okay, now, what are we doing here? What kind of analysis are we doing here? Are we doing descriptive statistics, correlation? We're comparing means, right? Even though it's analysis of variance, we're using the variability to compare means, which is kind of cool when you think about it, right? Kind of interesting you can do that. So we're going to one-way analysis of variance. By the way, why do you guys think they call it one-way analysis of variance? Anybody want to take a guess about that? Yeah. Yeah, I guess. Yeah. Well, how about this? We're only looking at one with respect to the numerical variable. We're only factoring it by one variable. We're only looking at, in this case, whatever this measurement is. Okay. Let me give you an example. Let's say that we wanted to, if we were taking hair color, right? Maybe 4 different hair colors, and we wanted to know whether there was a relationship between hair color and let's see, number of dates somebody gets, right? It's something silly like that, right? So if I looked at that, I have a numerical variable, number of dates, and I have a categorical variable, the hair color. Now, I'm only looking at the number of dates somebody gets with respect to the variable hair color. Well, how about if I wanted to include also, look at it not just from the number of variables, not just from the perspective of their hair color, but also their height, right? So now I'm not just looking at it from the perspective of one variable. I'm looking at whether or not height and hair color affect the number of dates somebody gets. Okay, so that you would call something called MANOVA, MANOVA, right? What do you think the M stands for? Multiple, right? Multivariate analysis. There you go. And that's really, it's just because we're only using one category here. One categorical variable is why it's one-way analysis of variance. Okay, so let's click in there. See what we get. Table comes up. The dependence list is our numerical variable. That's what we're going to calculate for our variability. Okay, I'm going to move that into the dependence list. Now the factor list is my group, whatever that happens to be, ethnicity or hair color or whatever it happens to be. So I'm going to move that factor group in there. Now, when I did it with the t-test, what happened when I did that? A little window popped up. It asks us to identify the variable, the values that that grouping variable could have. The reason why it did that is because in a situation where, let's say, ethnicity, You identify ethnicity by different numbers, 1, 2, 3, 4, 5, or 6. If we're just comparing two ethnic groups and we're going to do a t-test, SPSS needs to know what those are. If you're comparing Asian Pacific Islanders, Hispanics, or compare 2 to 6, right? In other words, what represents those two groups. In this case, it's going to look at all of them anyway, so it's not going to ask us which ones to identify which ones we want to compare. It knows we want to compare all of those values at the same time. Okay, it's the thing that's irrational is where you only have two groups. Why would pop up in a program that costs $1,000? Why they couldn't program it to really only two groups? It doesn't have to ask you which two, but that's you can ask IBM that. Okay, next time you pay your licensing fee, bring it up. Okay, so at any rate, so now I'm going to say okay. I'm not going to go into any of these options at this point. I'm just going to say okay. Okay, and of course on the Macs and in the latest version of the operating system, it runs. It's operating at a bazillion operations a second, but it still takes forever to happen in the Mac. Right, so at any rate, let's take a look at what we have. So let's see, between the groups, the sum of squares between the groups, 17.2. Sound familiar? Same thing we got, degrees of freedom, 2. Mean squares between the groups is 8.6. Within the groups, 25.2, degrees of freedom, 2. And the mean squares within the groups, 2.1. Sound familiar again? Yep. And the F value, 4.095, right? And now, instead of a critical value, SPSS actually gives us the p-value, our probability of being wrong. Let me rephrase that. The probability that you would get this result if there's no difference between these three populations, right? Another way of saying that, probably less accurate, is the probability of being wrong if you reject the null hypothesis. So as long as this is less than 5%, we're willing to accept that chance of being that level of error and reject the null hypothesis. So our significance, our p-value, is less than 0.05, so we reject the null hypothesis. Okay, so now what have we accomplished? We reject the null hypothesis. We accept the alternative hypothesis that at least, you told me before, at least two of the means are different. Now what? What's the next thing that we might be interested in here? Yeah, which two means are different, right? We only found that at least two of the means are all three different, or if it's a larger analysis, are all six different, and so on and so forth. So now we have to go back and we have to do another test to determine which of these means are really means of these populations are really different. So okay, let's go back up here to analyze. Are you guys keeping up with me on this on these machines? That's you, right? I'm not going too fast. Okay, let's go back up to compare means, one-way analysis of variance. And this time I'm going to go into post hoc test. Post hoc means Latin for after the fact, right? Post hoc. Okay, so let's pick these out. I think, what did we use before? Bonferroni, Tukey? Let's use Tukey. Tukey, Bonferroni, probably too much common. I'm not going to go into, we kind of just grazed on in the lecture on how these are calculated, what the differences are. But let's use Tukey. We'll go back and we'll compare it the other way too. And I'll say continue, and I'll say okay. Now SPSS is going to repeat the analysis. Okay, again, there used to be a movie that was on late at night on Channel 2, the Late Show or something like that, and they used to play a melody in the background called a syncopated clock. Da, 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 da. Right, it's kind of like the $64,000 question, and the only guy that understands what I'm talking about in this room is sitting over there. So never mind, but it takes a while on the Mac for this to happen. Okay, so anyway, on your machines it happened instantly, I'm sure. Okay, so let's take a look at this. Okay, now what SPSS does now, it does multiple comparisons, right? Well, it compares group 1 to group 2, and then compares group 1 to group 3. Okay, so let's see what the probabilities are that it came up with that these are from that we can reject the null hypothesis. Group 1 versus group 2, the p-value, the significance, the probability of being wrong if we reject the null hypothesis, mean of this group is equal to mean of that group, is equal to 0.223. Okay, too high, right? Okay, How about group 1 to group 3? Well, it appears the mean is there. If you remember back to the means, one was 1.8, the other was, I think, 4.4. That was the biggest difference or biggest gap. So it seems natural that that would be the one that if there's only going to be one pair that's going to be significantly different, that would be the one. Now, SPSS continues on and does a comparison of group 2 to group 1 and group 3 to group 1. And in fact, those comparisons we can't reject the null hypothesis. And then it repeats group 3 to group 1 and group 2. It actually does every permutation, even though it's kind of like double work, right? Because it does it twice. But you can see it comes out to the same number. When it compares group 3 to group 1, it's the same as comparing group 1 to group 3. So you get the same result. So those are the two means that are different from one another with that level of confidence. Okay? So if you guys have an analysis that you need to do for your project that involves a categorical variable that has more than 2 values, right? And you're using that to factor a numerical value that's in your data set. Well, you're going to be looking at analysis of variance. Okay, so I have other sets of data here that, let's see, SPSS data files. There's another data set here, IQ data. Okay, can't open it because it doesn't understand how to open it this way on my Mac because IBM doesn't really get around to getting these things to each version to work until the next version's available. At least on the Mac anyway. You can hear it, you can tell I'm bitter, right? About how slow they are about to update stuff on the Mac. Okay, I'm going to open that in front this way. I think it should work. Okay, here we go. In this case, they're comparing the IQ scores. I don't think those are real IQ scores, right? They're a little low. Some sort of intelligence scores for 3 majors. Okay, and physics majors, math majors, and chemistry majors. And what I'd like you guys to do is, number one, think of it from the perspective of what are your assumptions? Homoscedasticity, are the variabilities of these 3 groups the same or different? Do they appear normal? So how would you know that? Maybe you should run descriptive statistics on these and get make a little a box plot, or get box plots, or get make normal distributions from them, or histograms from them, just to get an idea whether you think they're really normally distributed. And also it'll give you a shot at finding out what the means and the standard deviations for each of these 3 groups are. Right? So get a quick look at it. Use descriptive statistics, get a quick look at it, get a feel about whether you think you're meeting those assumptions, right? And then do your hypothesis test. Number one, say to yourself, write down or say to yourself, what's my null hypothesis? What's my alternative hypothesis? And what level of error am I willing to accept? What's my alpha going to be? What level of type 1 error am I willing to accept? Okay, and say 0.05 or whatever, and then go ahead and run the test in SPSS, and you see if you get the result. Okay, so you guys at home, you can download that also. So why don't you guys download that, save it to your desktop, and give it a try. Okay, and I'll give you guys about 5-10 minutes to download the file. Right, this file that I have behind me, IQ data. It's on Blackboard, right? Okay, under SPSS data. Right. Do the descriptive statistics first, right? Do a box plot, look at it, say, gee, let me see, am I concerned about the assumptions here, right? Make believe you're concerned about the assumptions. I know you're really not, but. Okay, how are you guys online doing? Have you been able to follow this? Okay, good. Somebody put their cocktail down for a minute and type into the chat box. Good. Thank you very much. I appreciate that. Okay, good. I'm glad to hear that. Okay, good. I think we're doing okay. All right, I'm going to give you about 5 or 10 minutes to work on that. We're doing on time. We're in good shape on time. Then you always move the box. Okay, so in other words, you go to options. You then go to explore. So explore things is not when you break it up into different groups. So, you split. In fact, it is when you break it up. So now we're always going to get it. Always going to get the box. But if we got more. Okay, catch up, you guys. I just wanted to show you I'm not making this stuff. When I say this stuff, I'm not making it up. I'm sorry to interrupt you. Go ahead, Ben. Go on. That's been off the air probably for 4 decades, I'm sure. Oops, I just made a mistake there, a monumental mistake. And I can't do anything about it because it's taking me 3 minutes to get to this point. Let me show you what I got, and you can compare it to how you guys did. Okay, so first thing I did was I went up to analyze. Where am I? Oh, you want to know something interesting here? This is cool. Now look at this. When I click on, I have the output window up. Okay, give you an idea of another bug that's in this version, right? I click on analyze. Where's the descriptive statistics? It's not there. Watch this. I click on the data window. Click on analyze. That's what you call a bug or an undocumented feature, as the IBM calls it. Descriptive statistics. Now, for our, it's going to give us our means, our standard deviation, standard error, right?
What I mean is you have a different data set.
Oh, I'm sorry. You're right. I got the wrong data set. Hang on a second. I got that. I got the other one open here somewhere. Here's the IQ data set. You're absolutely right. Thank you. Descriptive statistics. You can tell I'm not good at detail, right? I'm an idea man. I'm a big idea man, not detail. Statisticians need to be really good at detail, I think. Okay, real statisticians. Okay, so I moved the IQ score into my dependence list. I moved the group number into my, or the group number representing chemistry majors, physics majors, and so on into my factor list. And I'm going to just go ahead and say, okay. Well, actually, I'm going to go into plots. I'm going to tell it, give me a histogram as well. Okay, now it's already checked off in there. But really, I'm really mostly interested in the box plots. But it's always going to give me the box. If I go into Explore, it's always going to give me the box plots on the outputs. I'm going to click OK. Again, syncopated clock playing in the background. Okay, and let's see what I get. Okay, so here we go. It finds this 15 students, physics students, 15 math students, 15 chemistry students. All the data is valid for all of them. And let's see, mean for physics students, the mean is 35.8. For math students, 32. It's a bit lower. And for chemistry students, it's 48. So whatever this is measuring, this IQ test or this knowledge test, it seems like chemistry majors are doing pretty good on it, right? Okay, so automatically I'm starting to think there's not much difference between physics students and math students, but a big difference between chemistry students and both of the others, right? So what about variability? Well, let's look at the standard error, standard deviation or standard error for each one of these groups. 7.9 standard deviation. Standard deviation here is 6.9, and standard deviation here is 2.3. Big difference, right? So I'm a little bit uncertain about this, right? Because here, let's take a look at our box plot. Sometimes a lot easier to see this graphically. Have I ever played the video for you guys from the TED conference? I'm trying to think of his name. Hans Rosling, Dr. Hans Rosling. Right, he has a very interesting way of displaying health data, and I'm gonna have to play it for you. If we have a little bit of time, I'm gonna give it a try tonight. Okay, so at any rate, graphically, it's much easier to see what's going on here graphically, right? We can see that the median is much different for the physics majors, but I'm a little troubled now because the variability is so small compared to the other two groups. All right, but like I said, we don't care. We're just students. We're going to go ahead and run this anyway. We're not publishing this information. So let's go ahead and do this. Analyze. We're going to compare means. One-way analysis of variance. Okay, so there's our group numbers. Our IQ is in there. Group numbers in there. I'm going to click OK. I didn't check see if post hoc tests were checked off. If it is, it'll run it. If it isn't, it will go back and run it again. Okay, so analysis of variance. What's our F value? Okay, our score for analysis of variance is 20, right? And so now we're talking about something that has only 3 means and a total of 45 subjects and all told. So a number like 20 is a pretty big number. We're starting to understand how the magnitude of these numbers. Okay, so if I went to my table with 20, my that Agrestes table that I have here somewhere, right? Let's see. Let's give that a try. Let's just take a look at that. Press T. Okay, so we have three groups where our degrees of freedom for between the means is 2, and we have 45 subjects in the three groups, so that would be 42. So we'd be down here around 40. So our critical value would be 3.23. And what was our what value did we wind up with? Wound up with a value of 20. So we can figure that we're going to get a very small p-value, a very small probability of being wrong if we reject the null hypothesis. And in fact, SPSS says that the p-value is 0.0. It's really less than 0.001 is what they're saying here, right? Less than 0.1%. Okay, so we would reject our null hypothesis would be that the mean intelligence score for chemistry majors, physics majors, and math majors is the same. An alternative hypothesis would be that at least two of them are different. And in fact, we reject the null hypothesis and accept the alternative hypothesis. Now we run our post hoc test, in this case, Tukey, and we determine which of those groups are different. Okay, not surprisingly, when we compare physics students to math students, we don't get a significant difference, do we? Those are the two scores that were very close together, two means that were very close together. Physics students to chemistry students, that's statistically significant, right? And how about math to physics? Again, that we just reversed what we did above there. So not unexpectedly, we don't reject the null hypothesis there. Math to chemistry students. In that case, yes. So chemistry students, the mean for chemistry students is significantly different than it is for math students, and significantly different as it is for physics students as well. So we found two differences there. Okay. So, okay, that's interesting. Now let's take some live data that we've worked with before. Let's go to the NC birth data, North Carolina birth data that we have. There's a copy of it online that you can download if it's not hanging around your machine already, which you're probably using. Erase it, I guess. You can download that. And this time, I'm going to leave it up to you to choose two variables, right? One of them is going to be a numerical variable, and the other one is going to be a categorical variable that has at least how many values? At least 3 values. So you're not going to choose gender, right? You only got 2 values. So you wouldn't use analysis of variance for that case. You would use the t-test. Right? Okay, so you download analysis of variance, and I'm going to join you in on that in a moment after I give you a chance to get it on your computers and decide which variables you might use. Okay, good. Okay, while you're doing that, so I want to point out to you. Okay, you guys doing that? How are you guys doing at home? Okay, you guys managed to get the same output that we did here? Good. Yep. Okay, I want to show you guys something else. I need a way to do this stuff. Let's see if I can't figure this out. Okay. I don't know how well this is going to work. I'll give it a try. Okay, a few years ago, they were talking about buying a bunch of iPads and using them for these classes. And somehow or other, those iPads disappeared. Some got used for something else. And unfortunately, I put together a demonstration of there's something called ebooks. I'm sure you guys have come across that. You can download them from publisher and so on and so forth. One of the advantages of them is, besides the fact that you can get them on a tablet or even a phone or something like that, and they're portable and so on. You can search through them and so on. A lot of other advantages. They also can contain certain kinds of graphical information, interactive devices, and so on and so forth. Apple has something they call iBooks. Happens to be a bit more interactive than most ebooks are. At the time when I did this several years ago, ebooks had very limited capabilities in terms of being interactive. But this iBooks thing, which was free, you could create a book that included video and all sorts of interactive stuff. Okay, so I did that. Now this actually I put this up on Blackboard, a link to Dropbox, where you can, if you have an iPhone or a iPad, you can download. Unfortunately, I'm not. This is not going to be anything that's required for this course because obviously not everybody's going to have pay the Apple Premium for this kind of stuff. If you happen to have an iPhone or an iPad, you can give this a try. Obviously, it doesn't work as well on an iPhone because it's tiny, tiny screen and stuff like that. But on an iPad, it still seems to work pretty good. But it's a chapter on analysis of variance, and basically, what it looks like is, let's see if I can't demonstrate this. Okay. Okay. So let's see if I can't make this work. I'm going to go to iBooks. And I'm going to load it. That's what happens when you first open it the first time. It'll play that video that we started with. Oh, look, it's a mirror image. Isn't that interesting? Right? So anyway, it'll play that video. When it gets done with that video, it'll drop into the textbook, the 4-minute video, or you can just click done, and it will actually go right into the text. Don't make a liar out of me here. Okay, so there you are in the text. And you can actually, it's just, I keep hitting the wrong button down there. Done. Okay, click that, please. Okay, there we go. Let me get to the first page. Okay, there's the opening of it. Right, and you can go through this page by page. And there's various things, like there's a little thing over here where if you touch on it, it'll give you each of the assumptions. Right, try and imagine you could actually read that. I wonder if there's a way for me to reverse the view on this. Enable screen flash, show facts, auto flip new items. I don't know what that means, but I'll click it anyway. Yeah, I don't see a way to change that. There's no preferences. Okay, I'll have to live with this as it is. I don't know what reason they have for doing it. So you can get the different, you go through all the text that we had there. There's some more information. It's basically what's in that video and what we discussed verbally. There's our table. You can actually click on that and get it to open up in a separate window that you can expand. I won't bother with that now. Okay, and here's embedded in here is the actual video of the calculation that we just did, where we go through the entire Excel calculation. Then some more information on it. Then this is a version of the this is a recreation, a video of the same operation on SPSS, which we also did. And here is a representation of the output that you get from SPSS. And if you click on these things, hard to do without touching screen. If you click on these things, they will give you an explanation of what each value represents. Okay, there you go. And there's more. Okay. Tukey, this is the post hoc test, also a video of the post hoc test. Also here, the output from the post hoc test and an explanation of what the values are. Just click on that and it will expand on that. See what I'm saying about the interactive qualities of this that are not in ebooks? Unfortunately, like I said, we didn't get we didn't wind up getting it. And then there's a quiz. Then there's various kinds of quizzes. And this quiz, what you would do is you would take this description on the bottom and you would drag it over to, very difficult to do here, drag it over to what you think it is. I'm not looking at what these are, right? And tell it to check it. And I got all of them right. Well, no, you couldn't see that. Right? You could actually drag these to different devices back and forth. I'm sorry, I can't get this to do this again, so I can actually do it so you can see it. Okay, so here we have, oops. There we have sum of squares divided by sum of squares between divided by the mean sum of squares. So that looks like this looks like it's going to go, say, over here. Okay, and these others would go in different places. And then you can go down here and check your answer. What's happening is I'm touching other parts of the screen as I'm trying to hold it. I'm going to just move these over randomly. Once you've moved each one of those into place, you can go down here and check your answer. These are going to be wrong, right? Because it's wrong, you can clear it and try it again. There's also various kinds of multiple choice questions. Okay, and you can tell it to check the answer. Okay, that one's wrong. And there's other questions as well. And then eventually, a whole bunch of these things. Number correct, right, number wrong, and again, another output table that you can check. Just click on those and give you an explanation of what's there. And then finally, this is a PowerPoint of previous class analysis of variance. You can just click through the actual PowerPoint from the class, from the lecture for that particular class. Okay, so this, you can download this. There's a PDF version of this, and there's the iBook version of this. The iBook version of this is a Dropbox link. You can just download it if you go there from your computer, from your laptop, from your iPad or iPhone. You can download it. You'll have to download the iBooks program. It's a free app from Apple. Install that first, and then download this, and you'll be able to. The instructions are on Blackboard, and then you'll be able to actually go through this whole thing. So, but there's also a PDF version of this, which won't have the interactive elements, but it'll have all the other stuff. And the videos are available too. Okay, so and I'll get my mug off of here so we don't frighten people at home. Okay, so I'm going to open up our North Carolina database. Okay, let's see. I can't find it here. Here we go. Okay, so here we have a lot of variables, right? Okay, we have some numerical variables: mother's age, the weight gained during pregnancy. We have the weight of the infant at birth in ounces and grams, and then we have a number of nominal variables. Plurality, I think that's a number of children that were born during that birth, twins or triplets or something like that. The sex of the infant, obviously we know the sex of the mother, so we don't need that. Right? So the weeks of gestation is a numerical variable. What other nominal variable? Marital status. Marital status. Let's see if that could be more than one value, right? It could be married, not married, but it could also be divorced, widowed, and so on and so forth. Now, in fact, it's not. They only give us married or not married. Okay, so what variables did you guys choose to work with? Anybody want to volunteer? Sure. Okay, race of the mother and weight gained. Okay, so let's look at race of the mother. Where's race? Is that here somewhere? That's number 6. Okay, let's see how many values we have. Oh, we got lots of values there. Okay, so here's an application for analysis of variance and weight gain. So let's go ahead and let's do this analysis. Analysis, compare means, one-way analysis of variance. Weight gain is during pregnancy. And we're going to factor that into values for race of mother in here. I'm going to go ahead and just click off one of these post hoc tests. So we save a moment or two because we're running out of time. I'll click continue. You didn't do the post hoc? Oh, you didn't bother? Well, hang on a second. You might have been, perhaps we can't reject the null hypothesis, and we might not even want to run the post hoc test, right? So not doing the post hoc test right away might be the right decision, right? So okay, let's see, take a look at what we have. Warning, post hoc test cannot perform because at least one group has fewer than 2 cases. Well, what can we do there? One of the things that we can do there is we can create a new variable that we can either filter that variable out, or we can create a new variable that only has, let's say, instead of all 8 ethnicities, has maybe the 5 that we're interested in, or something like that. So we got to either set up a filter, or we can create a new variable that ignores that particular case. What was that, like Asian Pacific Islander or something like that, right? So let me see if it doesn't look like we would have been able to reject the null hypothesis anyway, but because our f value was 0.74 and our probability of being wrong if we reject the null hypothesis was way greater than 0.05. Okay, so it didn't seem like there's a significant difference in the weight gain for any of these ethnicities. So that tells us something right off the bat. We learned something, even though we weren't able to prove what we wanted to, that there was a difference. We did learn something anyway. Okay, any questions? You know, I probably, the way I would handle it is I probably create a new variable. First of all, which one is the, okay, so let's see, transform, compute, recode it to different variable. Okay, so now I'm going to take, which one is race and mother? Okay, my output variable is going to be race 2, let's say, name. Okay, and I'll say old and new values, right? And so now what I might do, you happen to remember what that variable was? What that value was for them? Yeah. Yeah, it was 2. Okay, so I might say for the old variable, 1 is equal to 1, right? What's that? I'm sorry. Yeah, whichever. That's 4? Yeah. This is 4. Okay. For 2, I'll make the new value 2. For 3, you can also do this by range. Right? I'll make the new value 3. I'm ignoring 4. I'm going to go to 5, make the new value 5. So it's not going to copy over the 4s, right? Or if, in fact, if I really want to, I could just make what was 5 before, make it 4 now. Maybe I don't want to play around with that because that's going to mess things up. Okay, make a new value 5, 6. I'm going to stop with this one. Okay, so I'm copying over all of the subjects from the new variable. Okay, and I'll say change. Say, okay, I did this quickly. Hopefully it works out. Dun, 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 dun. Okay, so now let's do this. Let's do this again. Analyze, compare means, analysis of variance, weight difference. This time I'm going to use the new race variable. Okay, I'll say okay. Say make sure post hoc is turned on. Yes, it is for 2. Say okay. One more moment, then you guys can bail out. This time it actually did the post hoc test because it didn't have that problem with the group size. Okay? 1, 2, actually, I'm not sure why we only got 1, 2, and 3. Is it possible the other groups didn't have any values at all? See, I only see between groups. Well, I'll take a look at it tonight, and I'll post something in the discussions and stuff like that. I'm not sure what happened to groups 3, 4, and 5. I didn't move them over. What happens? I probably didn't hit change or something like that. Yeah, like I said, I'm not good with details. But you understand what happened there. I created a new variable. I said, okay, all the ones go over, all the twos go over, all the threes go over. Up fours, I don't want them because we don't have enough in that group, in that category. So I'll move the others over until I have a new variable with values that are all valid for performing the post-hoc test. And you can also recall, you can actually do calculations. For instance, if you know height and weight, you can make a new variable called BMI by actually doing a calculation for each subject based on their height and their weight. Okay. Or if you want to take something that's a numerical variable and you want to change it into a categorical variable. Like for instance, how do you determine if somebody is diabetic? Well, if their blood sugar is over 100, they're diabetic. If the blood sugar is under 100, I'm just for argument's sake, it's obviously an oversimplification, but if their fasting blood sugar is over 100, you're diabetic. If it's under 100, you're not diabetic. So if you want to turn their actual blood sugar into a categorical variable, diabetic or not diabetic, you can set up a computed variable that looks at their blood sugar and then creates a new variable that if the value is 99 or less, put a 1 here. If the value is 100 or over, put a 2 here. So you change a numerical variable into a categorical variable. But as you go through this and start working on your project and deciding what kind of data you want to work with or what kind of data we have available for you to work with, this will be a little bit, you'll find ways that you can use the SPSS to help you with organizing your data that way.